Welcome again. Recording, and share my screen. And today we're going to start chapter 5 of the book. Okay. Chapter 5 is about building assembler programs. How we did already start building assembly programs, but this is more formal, shows how you start, step-by-step approach, and we go more detail. You're going to discover that most of the things here are build on what we did in the past few lectures. It's going to be easier, however, I anticipate. So it's about visualizing a program. How do you see a program? So when we say design, and I'm going to be asking a lot of these types of questions. Design an embedded system. Okay, design. As you saw in the syllabus at the beginning of the course, this course is tied to the design component from our student learning outcomes, the ABIT. Well, they call them the ABIT student outcomes. They're not only for ABIT. It's most of engineering accreditation commissions today look at the design component. It's one of 7 components. So this course we're studying here, the embedded systems, is one of the main courses that measure the design component in our engineering curriculum. Okay, so we concentrate on design. We're going to have many design questions. Well, starting from the design project, going through in the exams design problems. So when I say design an embedded system, the design here is made of 3 main components. First, we have the circuit or hardware design. 2, we have the embedded software design. Then we have the mechanical design. And about mechanical design here, as electrical engineers and embedded engineers, we talk about high-level mechanical. For example, if I ask you to design an embedded system to count the number of people entering a room, for example, in this case, you need to show me these 3 components: the hardware design, the embedded software design, and the mechanical design. Let's start with the easiest. The mechanical is the easiest. So you say, okay, I want to do it this way. This is the room. This is the room. And I want to count the people, the number of people entering the room. And this is the door. I don't know, I'm not good in drawing. And this is the door. I want my mechanical design is to have an infrared IR transmitter here, okay, an IR receiver or receiver, okay. This is the mechanical design. This is how you want to set up your sensors. Then you can say, okay, the electrical design, I'll have a box here with the electric hardware. Okay, and this is connected to a microcontroller. So this is the mechanical design. Then if we go to the electrical design, this is the IR sensor, the IR receiver, whatever. Okay. Let's assume it is a digital. There are analog ones, digital IR receiver. So I connect it to my microcontroller. I have a 16F877A microcontroller. Okay. I've connected to port B0. Okay. And it's just a counter, right? So whenever there is somebody enters, I get a pulse. For example, let's imagine that this is how the sensor, and I count the pulses. So this is simple hardware design. If we want, okay, when somebody enters, I can do an blink an LED, for example, if this is part of the requirements. Okay. If it's a red or a green LED, then you compute the resistor, right, to protect the LED and the microcontroller. So this would be the electrical design. Then we come to the embedded software design. It would look, I'm talking about not software. I don't want to see code here. I want to see a design, you know, just one, like you look at a schematic for a circuit or a design for, I don't know, a building. You look at drawings, so you as an engineer understand what's in there. So there are many ways to visualize software design, okay? One simplest way that you experienced during, well, I guess your introductory programming classes, using flowcharts. So you say, okay, you know these symbols, start, and a rectangle is for a process, right? And diamond for a condition. What else? So using these symbols, you can draw your design. Okay, you start first. Then you do, what do you do? Well, depends on what level you are asked to do the design. Is it high level or lower level, going down to the register level? This is something we can talk about later, but for this particular example, the software that you want to write for the embedded controller to do is, first you need to initialize all ports and I/O you want to use. For example, in this case, port B, right? Port B0 input. Depends. If we want to go low level input, we can write this, or initializing port B as input. Let me do it easier this way, right? So this is port B0, this is port B1, for example. So set for port B0 as input, port B1 as output port. Then you go and check if there is a signal on port B0, yes or no. If yes, you want to do something. If no, you want to keep checking that again. This is no. Okay. If it's yes, okay, there is a signal. Okay, I should have a counter to increment. Maybe here, initialize a counter. Okay, if yes, you go increment the counter, right? And what? Blink the LED. On port B1. Then what? And then we go back again and check port B0 forever. Well, if you were asked to do a display, you can have a 7-segment display here with the number of people, 2 7 segments, right? And when we get to interfaces, we can see how to interface these 7-segment display, 7-segment display. Maybe you want to display the number counter on the 7-segment. Then you go check for port B again, forever. So will you have an end here? Many of you forget and do end, and this is wrong. Okay, this is wrong. In embedded systems, you always should have an infinite loop. You should have a software running forever. Okay, don't forget that. So this is a software design. This is a way to visualize a software. So if you are a design engineer, okay, somebody's doing what? Okay, is this hacking or what? Is this what they were talking about? Is somebody doing this? Shabab? Okay, clear. And I heard, في security bugs صايرة where's the chat? Okay, I'm going to stop sharing for a second to check what's going on. Okay, annotation. I'm going to disable it for you guys. Anybody? Any outsider? Any outsider?
لا دكتور بزبطش يفوت حدا ما عندوش
مين اللي خربش على الشاشة هلا؟ واحد بيلعب صح؟
والله ما
خربش
بعرف.
على الشاشة؟
في واحد خربش على الشاشة.
أنا كنت أجرب، فكرت ما بيطلع عندك.
يا حبيبي عليك. طيب نشفت دمنا لأنه قالوا هاكرز صايرين يدخلوا يعني.
لا هو على أساس
طيب.
حكونا ما بيطلع عندك.
لا بيطلع. Okay, don't do it again. Okay. طيب. ماشي؟
دكتور.
Yes, تفضل.
We can have 2 IR blasters next to each other, and based on which one pulses first, we can determine if someone is entering or leaving.
Exactly. واحد على يعني قبل واحد بعد. Yes.
Yeah.
The people. أنا بس okay. يعني we're gonna come to that. Look more into sensors, how to use them. Thank you. Good idea. But the goal here is to talk about designing embedded systems. Okay. So these are the main 3 components you need to look at. The mechanical design. It's not a real it's a mechanical setup where you want to put your sensor. So Ayman is talking about حط sensor بالبداية على مدخل يعني قبل 10 سنتي واحد بعد 10 سنتي, right? So إذا الأول عد بعدين الثاني, so people are going this way entering. إذا الثاني عد بعدين الأول, so people are exiting, right?
Exactly.
Yeah. And yeah, the electrical design, the circuits, you draw your sensors. Where is it going to be connected? Well, this is digital, but if it's analog, you cannot do it. You cannot connect it to port B. You need to connect it to an analog port, okay, like port A. Okay, then a 7-segment. Okay, 7-segment display. How are you going to connect them? To what ports? If you were using a resistor, what's the value here of the resistor? Tamam? So the embedded circuit, the hardware, including the microcontroller. If you're asked, okay, you need to say that I have to connect to the VDD, مثلا 5 volts, وبعدين ground, right? And you know, of course, no need to tell that, okay, the ground هذا is the same as هذا, right? So انت بالطبيعي لما تيجي بدك تسوي circuit وتجيب بطارية مثلا زي اللي عندي هاي 9 volt battery, right? وعندك 5 volt power supply, so you connect the positive here, right? And negative, what do you do? مثلا هذا LED كمان عندي أنا هون مثلا موتور، وهذا MOSFET، وهنا عندي موتور بده 9 فولت، right؟ وهي ground. What does this mean? إنه هاي negatives كلها when I draw the ground عشان ما أسويش complexity بالرسمة. This means إنه the ground of the negative part of the voltage supply is going to be connected مع negative part of this battery, and here, and here, right? And here. So a circuit, this is what's going to be the reality. راح يكون عندك سلك واصل هذول كلياتهم وحاطهم على نود على البريد بورد. تمام؟ Okay. Trivial, but sometimes people forget. Even لما نيجي نعمل okay عندي هذا كنترولر وهذا كنترولر ثاني، اوكي بدهم يحكوا مع بعض سيريالي، هذا بده يودي سيجنال ترانسميت على الريسيف هون. اوكي well this is a voltage level reference to this microcontroller. بس هذا what is the reference؟ المفروض الجراوند تاع هذا يكون واصل مع الجراوند تاع هذا، اوكي عشان يكون لهم نفس الريفرنس. Well, master clear. Do I want to connect the master clear? Okay, so if you're asked to do that, undo. بس نخفف العجقة شوي. Okay. ماشي. So don't forget, if you remember while you're walking around in the embedded systems lab or innovation lab بالجامعة, you see a lot of flow charts, right? And you see a lot of mistakes like this, people having an end. In embedded systems, you should have an infinite loop. Don't forget that. So this is a way to visualize the program, software design. And this is the first part of our chapter here, okay? How to visualize a program. Many ways. After that, this is our first part. We're going to talk about visualizing the programs, different ways. Then we're going to go into more deeper in assembly programming, how to do branching and subroutines, how to do delays, lookup tables, logical instructions, okay? How to optimize an assembly program, and look at simulators. We already did that. So for an example, of an embedded software that you represent. ليش هاي انتوا شايفين الثلاجة ولا لا؟
بلا مبينة.
اوكي طيب. So هذا مثال على refrigerator، ثلاجة، and you know الثلاجة اليوم فيها controller, right? And that's how new devices save power. It's not just analog. زمان كان في شيء يتمدد بالحرارة، بس يتمدد بالمس إشي، صح؟ بتشغل الكمبرسور، بتبرد، بتقلص، بفصل، صح؟ Right? كان mechanical characteristics. Now we have controllers, sensors that make things more precise. So a fridge, a simple design of a software would look like this. For أنت ثلاجة أنت you want the temperature inside the fridge to be مثلا 0 Celsius, okay? So there is a temperature you want, okay? This is the demand temperature, okay? In control, we call it the set point. دارسين control انتوا ولا لسه؟ set point. طيب. And there is an actual temperature. Actual temperature الآن أنت قلت اعمل الحرارة 0 بس الحرارة الآن 10 سلسيوس. This is the actual. And where do we get it? This one from? From a sensor, okay? You get this from a sensor. Where do you get the demand temperature? Well, مش أنت لما تفتح الثلاجة بيكون فيه زي potentiometer or هيك wheel or I don't know what they call it إنه أنت بتغير الحرارة أو push buttons صاروا اليوم you raise the required temperature or you push it, you decrease it, right? From the user through a potentiometer, through push buttons, etc. So first, the microcontroller, we're talking about software, right? A software program that's going to be run on a microcontroller. First, the actual temperature inside the fridge is red. يعني, so أنا عندي this sensor is connected. Okay, if it's an analog to port A0 مثلا, you read it. You read the analog to digital converter on port. We're going to see how you do that. At this level, you don't need to know the actual instructions to do things, but you need to know what you should do. So the microcontroller reads the sensor to know what is the temperature inside the fridge. Then it reads the demand temperature, the set point that the user wants. Then it compares. If the actual temperature is greater than the demanded temperature, معناته حامي أحمى من ما أنت بدك صح? It is the temperature is higher than what you want inside. If yes, you go activate the compressor that starts cooling. Okay. If no, you switch off the compressor. So this is a very simple control loop. If you study embedded control, you study PID control, but this is an on-off control loop. Okay. So you turn on the compressor, then you check again. If it is, well, let's do it one loop, one cycle. If it's larger, you turn on the compressor, start cooling. If it's not, and the compressor was on, you turn it off. Because why do you need to keep cooling while the temperature is not more than what you need? Then you check. If the actual temperature is greater than the demanded temperature كثير, okay, يعني 20 درجة مئوية more than what you want, هنا مثلا درجتين, you turn on the compressor, you start cooling. بس أكثر بكثير, yes, you may want to do an alarm. There is really something dangerous going on. If it's not, you go back again. Read the actual temperature. بردت شوي, بجوز بردت. Okay, but still larger than the demand, you keep the compressor on. لسه مش كثير. Okay, you go back until it goes below the demand, then you turn it off, right? And so forever. Very simple way of visualizing a program. Sometimes you need to go deeper. But this هذا بسموها high level requirements. تمام. In industry, this is well known, and I'm not going to go very, very, very deep here, but in industry, they have engineers just to put the requirements. These are called requirements, software requirements. So one of the simple ways to put software requirements is to just write, okay, reads the actual temperature. 1, 2, read demand temperature. Okay, 3, check if greater. If true, go back to 2. You write like something like pseudocode, and this is what used to happen in the industry. But then هذا requirements engineer or control engineer, if you want to call him, okay, send this pseudocode or this design visualize to a software engineer who turns these requirements into software. يعني code move letter to W, well, or C والى آخره. بيعمل software. Okay, then we go on from there. And I used to really spend a lot more time on this topic in class, and I have real documents from the industry I can show. But since this recording is public, if some things are confidential, I cannot share it in public. Okay, so this is a way using flow diagrams to show how your program would run. So when I ask you مثلا في امتحان show your design to do blah blah blah, one of the components is the software design. Okay, it doesn't mean write code. And I'm going to get this question a lot. Do you want the code in C or assembly? Well, no code, no C or no assembly. It's just a way to visualize how the program would run. Another way is a state diagram. Well, let me ask this question. يعني ممكن واحد أو اثنين يجاوبوا on behalf of others. درستوا flow chart صح؟ لما أخذتوا أول لغة برمجة بحياتكم صح؟ قبل ما تبلشوا تبرمجوا, you think how the program is gonna work. تمام, أنت اللي طالع قدامي. درستوا flow charts?
Yes.
Okay, thank you. So it's not a new thing. State diagrams is another way. وهذا كمان درستوه وين؟ بالlogic I think. Right?
بالlogic.
تعلمتوا كيف تعملوا state diagrams, state flows صح؟ flip flops, state machines.
Yes.
الميلي والمور.
ايش هو؟
الميلي والمور كان دكتور.
Yes. آخر chapter I think it was. You check a bit, the bit, right? Zero input is 0, the output is 0. You stay here if it's right. If the input is 1, you go here, right? State diagrams. So you learn how to do it in simple hardware, flip-flops and things like that. Well, today's modern tools also have these built in, like MATLAB Simulink. Inside MATLAB Simulink, you can actually, and we're doing this in the Embedded Systems Lab. Well, this is another way, of how to specify your requirements. There is something called model-based control or development. So the controls engineer in this case, instead of writing pseudocode of flowchart وبعدين يجي software engineer turn it into software. Okay, the software control engineer can use model based مثلا like in Simulink. بيجي بيحكي okay, read port B0, and we started doing this semester in the Embedded Systems Lab, and then okay. And take this reading to a switch. If it's larger than 10, for example, okay, return a 1, else return a 0, okay, and this, okay, and you draw blocks, and you give it, this is the requirements, you can simulate it, you can simulate your program. See on pre-collected data or whatever, see how it works, your code without writing a single piece, a single line of code. And then you give it to a software engineer who does autocode generation and turn this graph into C, for example. Okay. طيب. بطلت الخرابيش تطلع. I want to show it, but how do I erase it? pointer options, razor all icon slide. Okay. تمام. So يعني regular Simulink blocks is another way to visualize your program. Another way is using state diagrams, and also this is also implemented in MATLAB Simulink. You just add a state flow and you start getting like these bubbles, write in it a few lines of code if you want to do something, then write with tools you say if the condition, the sensor says that the door is open, go to the second state, keep doing this forever, and when something happens, go here or here. So this is a simple example for a washing machine. Well, how does a washing machine work? If you want to visualize the program running on the washing machine using normal flow charts like this, راح تصير عندك عجقة. Okay, يعني راح تقول له okay, start do the initializations, door open, or يعني خليني أخربش شوي. Okay, if I want to do this exact same thing using flow charts, you can do it. But it's going to be a little more complex. User initiates door closed. Okay, you need to do initializations for all the sensors or whatever, but then you need to check door closed or not. No, you keep checking for it. You don't do anything. If yes, okay, you go turn on pump to fill water, right? بعدين full level detected, بعدين you check. خليني أجي هون. Full level. If no, you keep doing this. If yes, right, you go heat the water, turn heater, right? Then you check, did we get to the required temperature? No, you keep turning the heater on. Yes, see كيف قديش في عندك conditions و checks وإلى آخره. a little complex. So there's an easier way to visualize your program using state diagrams, something like this. You're ready, start ready. You stay in this point until the door is closed. So if you have a sensor that detects that the door is closed. Once the door is closed, you move to another state. In this state, you keep filling water. Okay? You don't exit the state until a condition happens. Turn on the pump, fill water, or open the valve with the water أصلاً لحالها جاية. Okay? Once the condition, the sensor that detects the water level inside the washing machine detects we're full, we go to start heating the water. خلاص, we're done with fill. We turn off we close the valve or the pump. We go to start heating. Well, if this doesn't happen within a certain period of time, mمكن you check it after a timeout, within 2 minutes, 3 minutes, 5 minutes, whatever. It doesn't happen, you go to a fault and you display a fault on the screen, right? Or on the display of the washing machine. But then you start heating the water, you turn on the heater, keep checking 2 things, timeout, or if the temperature, using a temperature sensor, is reached, then you start washing, and blah, 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 okay? So states, you can represent your software using this way. And actually, as I said, a lot of tools today, like MATLAB Simulink, offer you to just really draw these things and then convert them into code, right? And if you allow me, I can show you a simple type. I would, I'm going to be searching. I'm going to stop sharing the screen for a second to find that, to find the simple file with this example. Okay. Okay, I'm gonna share again. Well, this is some work I did in the past, a patent for a drone. And see, this is my code. It shows, okay, that I need to read the desired something from a sensor, compare it, do something. Well, there is something inside this box deeper, okay? However, you just push a button. Well, maybe I opened the wrong file. You push a button and you get the C code. Okay. Nevertheless, I may have, well, if you want to look into this more, just Google model-based development or model-based control and you'll find. This is a simple way of visualizing your programs using state flows. Yani, for example, for conditional and branching, the other topic, yani, we're going to do an example. I think we can do an example today. Bit test F and skip if clear or skip if set. These typically yani, appear here, right? How do you check if a button is pressed or if two numbers are equal, right? You couldn't subtract them and then check a clear flag in the status register, okay, or a zero flag. And if it's true, you go do something. If it's not, you skip these. If it's not true, you can keep going, right? A way to visualize your program. Working with bits is well, a simple program, high level to check if a button connected to port B bit 0 is pressed, it's clear, well, depends, is pushed or not. Either you skip this instruction, go to blink an LED somewhere, or you don't skip it and go to somewhere where you just turn on the LEDs solid. Branching on status register bits. طيب. I want to do with you some simple program that does this. ورايت code مع بعض. So if we are to design an embedded system to blink LEDs, first, and then we do conditioning. To blink LED, port B, I want to design a system that connects port B0 to port B7, going 1, etc., to 8 LEDs. Okay, I want to start blinking these LEDs. And last time when we wrote an example in MPLAB, we just turned on the LEDs. Now I want to blink them. On, off, on, off, on, off. For example, half a second on, half a second off, forever. Just keep blinking them. How would I do this? And if I do the flow chart, first I need to port B set
حط port B output.
Exactly. Then what? I can say turn on LEDs, right? يعني اكتب على port B, sorry. Turn on LEDs depends, turn on LEDs, which is what? Port B, write in it 0xFF, right? Well, so to set port B output command هون, يعني we can say TRISB, right? Write in it 0x00. Then delay, well, خليها أسهل. Delay for 500 milliseconds, نص ثانية صح؟ بعدين turn off LEDs in port B 0x00, right? Then another delay for half a second. $500 milliseconds. Then what? You go turn it on again, right? So it would look like this. Turn on, delay, turn off, delay, right? Keep doing this forever. Now we know how to turn on, we know how to turn off. How do we do the delay? We didn't study interrupts yet, but when we studied the instruction set, we know that every instruction takes a certain amount of time to execute, right? Yeah. And we had a question about this in the quiz last time. See, every instruction here has a number of cycles to execute that it needs, instruction cycles to execute. And we know that each instruction cycle is how many clock cycles? 4 clock cycles, right? 4 clock cycles that we get from the oscillator. And the oscillator frequency is a number we know, so we know that each instruction takes this much amount of microseconds, for example. One of the instructions, well, these affect registers, yani add W, and W, clear F, they affect registers, but we have a no operation instruction, if you see down here, right? No operation, that does not affect anything. It just wastes 1 cycle. We can use this to do delays, right? We can use this to do delays. So let's use it. So لو أجي أكتب برنامجي, let's do it in MPLAB. How about this? وبنعمل الحساب يعني. Let's start a new project. Close this one. Project. Let's start a new project. And we want to run it on the 77A microcontroller. Okay. And we want to save the project here somewhere. Let's say in a new folder called class demo 3 blink LEDs. Okay. So let's do it here and call the project blink LEDs. Next, finish. And we create a new ASM file, do a save as, put it in the same folder Blink LEDs, add it to the project and call it Blink, for example, blink.asm. Save. Okay, what we want to do here is to, and we draw the flow chart, right? We need a few registers to deal with. So the status register to switch banks, status was the address number 3, right, in the data memory. And we are going to deal with port B register, which also equates address number 6 in the data memory. TRISB is also address 6 in the data memory, but in bank 1, and we can add other stuff later. We start writing our program at origin 0 in the program memory, and the first instruction, easiest to say, go to my main program, right? And my main, we can have it somewhere here, my main at origin whatever 0x20x, and we write our first instruction here. What do we want to do? We need to make port B, as we saw in our flow chart here, that we need to make our port B as an output port, right? So how do we make it an output port? We need to go to bank 1 and write in the TRISB register zeros, right? Yeah. So how, okay, band select bit, well, حافظينه خلاص, number 5. Well, خلينا نكتبه كمان. Bank select bit equates 5. So we bit set F, we need to make in the status register bit, the bank select bit, we need to set it. So we went to bank 1. Now, if we write to address 6, then we're writing it to the TRISB, direction register of port B. What do we write in it? Output means 0, so we clear it. So we say clear F TRISB. All the bits, right? All port B pins are output. Then we go back to bank 0. We clear the bit number 5 in the status register. Bit select, bank select bit, we clear it. Back to bank 0. Now we are at bank 0. What do you want to do? We want to turn on the LEDs, right? So we move lateral to W. We cannot write directly to F, right? To memory. We put it in W, then we move it. What do we write? Once on all the bits to turn them on. Well, again, this is if the design is like this, right? If the design, the electric design was different, you can have an electric design that is like this, right? Port B 0, port B 7, and these are the LEDs. In this case, the software design is completely different, right? You need to set port B as input and, output, but you write to it zeros instead of ones to turn on the LEDs, right? Okay. So depending on your hardware, how you're going to connect your LEDs, you write your software. For our electric design, a 1 will turn on the LEDs. So we write 0xFF, right? we write ones to all of the bits. Move literal to WFF. Then, oops, what happened? Then we write, move this W, move W to F, where? To port B, which is address 6. So turn on all LEDs connected to port B. Right? Then I want to do a delay for 500 milliseconds. تمام? Delay. Well, يعني I don't know how to do the delay yet. Delay 500 milliseconds. We come back to it later. Then we turn off the LEDs by clearing port B, right? Turn off all LEDs connected to port B. Then what? Then we do another delay to keep it turned off for 500 milliseconds, right? Delay. Then what do? We turn it on again. So we say go to forever. مثلا forever is a label that will be here, right? Then nothing any left. We end our program. So it is 10:53 already. Next time we will write the code to do this delay. We will do instruction-based delay by wasting time. Okay, for 500 milliseconds, we will build on using the no operation instruction. Well, a no operation instruction, how much time is going to take? In our case, the frequency oscillator, the oscillator frequency I have on my board is 8 megahertz. So the one no operation is going to take, if your oscillator frequency is 8 megahertz.
نص ملي سكند.
No operation, how much time?
نص ملي سكند دكتور.
لا 500 مايكرو. Yes,
well, you calculate it. So one instruction cycle equals what? 4 time for one instruction cycle equals 4 times time of the oscillator, right? The time of the oscillator time is 1 over frequency of the oscillator, right? Equals 1 over 8 megahertz equals 0.1 نص الربع صح؟ 125.
Yes, 125, yes.
0.125, something like this, microseconds, right? Then time for instruction cycle equals 4 times the t time for the oscillator, and this equals 4 times 1 over 8 megahertz, and equals what? هذه بتصير 1 هاي بتصير 2 صح؟ 0.5 microseconds, right? So this no operation, because it takes one instruction cycle, this is only 0.5 microseconds. So we need to repeat this NOP how many times? 1,000 times 0.5 microsecond. So 2,000 times, right? Well,
على 1000 بخليها نص ملي.
but then so well, if you you need to multiply it. So a millisecond, how many microseconds? 1,000, right?
Yes.
You multiply it by 1,000, and this is it will become 0.5 milli. Then كمان
100,000 مرة بنعيد. 100,000 مرة.
okay, so 100,000 مرة. How do we do this 100,000 times?
Counter loop عبي counter 100,000
Well, this is the beauty of understanding the hardware. What is the counter? What is gonna be able to hold a number 100,000? Knowing that all our memory locations are 8-bit. See, we need to look deeper. 8-bit can hold a number of 8-bit, maximum 8 ones, which is FF, which is 255. So this is what we're going to look into next time and do the math and compute the exact delays. Okay, we may need more than one loop. Okay, a loop inside the loop inside the loop. Okay, to do that. So I'm going to save this. Well, building it will save it. It's gonna, I think it's gonna give me successful because I don't have any syntax, but it is not gonna do the right thing when you run it. طيب, if no questions on the topic, I'm gonna end the recording and you can stay for to chat about anything in the course if you like. Okay, where is the recording button? Stop sharing. Okay, no questions. Thank you everybody. See you Tuesday.
مرحبا دكتور.